welcome, and we'll get started in just a second or two. A reminder, again, please keep your cameras off and all that so I can see my screen. We'll get started in just a sec. Again, if you have questions, you can type it in the chat box down there. Again, we'll start here in just a minute. Give everybody a chance. We should be lecturing on Chapter 13, Equilibrium. Again, these should follow the notes that you have that you were given as we were doing it in class. If you don't have those or can't find them, again, they've been posted also on our Canvas site in the module section. You can find lecture notes for this one, and then for all future ones as well, you'll be able to find some lecture notes in that area as well. A reminder that again, this is being recorded, so any information that you see on the screen will be recorded in that video, and you'll be able to, if you want to look at it again once they get posted. It does take a little bit of time again to process those videos and get them up there onto our Canvas site, but eventually they will be up there, and anything I write on the screen, anything we work out, it will be captured on the recording and stuff like that, including any voice, video, or anything like that. So again, try to keep all that stuff off so you don't find yourself in the middle of anything. And you can go back and look at all this stuff as well. So if you do miss something as we're going through this, you can go back to those recordings and sort of take a look at it again, and you'll be able to see everything just like you see on the screen right now. Before we get started with sort of lecturing, any questions on the course or anything like that? Before we get going, we met on Tuesday. We took care of a lot of business and stuff like that. Any questions before we kind of get going on lecturing? And a reminder today as well, there's going to be a lab session after lecture, and we'll talk a little bit more about that towards the end here of lecture. But scheduled for days should be the, I have it in front of me, but I think it's the kinetics activity, I think is what it's called. And again, that's mostly an Excel sort of assignment, but I will open up a lab meeting starting around our normal time after this one. So we'll take a little break after we're done with lecture, and I'll start the lab, and we'll talk a little bit about that sort of experiment, what you need to do. It's mainly pretty much an Excel sort of experiment. You're going to do all graphs and stuff like that. So yeah, so in terms of that, probably if you need me, the best way is to email me. We can definitely do some virtual office hours. I haven't really figured out when we do that, but to be honest with you, I'll be on here for lecture and lab pretty much every Tuesday and Thursday. So if you do need me, you can just let me know, and then we can set up a time in between maybe lecture and lab or after lab or something like that. On these days would probably still be the best way to do that. So I'm still kind of working that part out, but definitely can still email me. And if you do need, we can virtually meet and you can ask questions if you need. I'll try to narrow down maybe some times when I'll have some virtual sort of office hours. Maybe you could kind of sign up and do that. Other questions or anything like that? And again, you always can email me just like normal. I still check it even more now, I think, but I check it several times throughout the day, every day, and through the weekend and stuff like that. So you can. Yeah, so if you want to ask a question, you can do one of two things. You can type it in the chat. There's actually, I think, there's a little button in the participants where you can raise your hand virtually, I think, if that's what you're asking. And I'll put like a little hand up that I'll be able to see in the participants sort of window on my screen. And then I can just ask you your question if you want, or you could type your question. I do have the chat open, so I'll be able to see every question that kind of comes by, and I definitely will get to it. And when you ask questions on the chat, you can do it either to everybody, as you can see, or again, you can type me something that says private, and I could type just privately back to you and answer and stuff like that. So you can do it either way. Again, I think there's a place where you can kind of raise your hand if you want, and then I could come to you, and or you could just type what your question may be in the chat. Any other questions or anything like that? Okay, so I did want to start lecturing. So it's been a while for us, but I think this is where we're at, if I'm not mistaken. So if we're not, let me know. I think this is perhaps where we left off. I don't think we talked about reaction quotients. We did talk about, just to review, right? We talked about equilibrium. Let's go back, maybe I page, get something blankish. So we talked about, she's not to scribble on. We talked about equilibrium, and a couple of reminders, right? We have, when we're talking about a reaction that's at equilibrium, it involves a certain type of reaction, which is a reversible reaction. And let's just call this 2, 4, 2, 2. And when we have a reversible reaction, what that means is, as we talked about, it means that at some point it will reach chemical equilibrium. And what chemical equilibrium means really is it has to do with the rates of the reaction. So it is the rate of the forward reaction and the rate of the reverse reaction, which is when it's going from products back to reactants. Basically, those rates will equal each other. So the rate of the forward reaction will equal the rate of the reverse reaction. And that's what it means when something has reached chemical equilibrium. Again, it doesn't mean that we have exactly the same amount of each of those guys, the reactants and the products on both sides. It just means that the rate of the forward reaction will equal the rate of the reverse reaction. Now, when we do get something that does equal equilibrium or reaches chemical equilibrium, we can write the equilibrium constant, and it is basically the concentration of our products divided by the concentration of our reactants. And unlike kinetics, we actually do use the coefficients here as those exponents. So we would go K is equal, in the above example, C squared times D squared divided by A squared, and I think I scribbled a 4 in front of that, B to the 4th. And so unlike kinetics, we do actually use the coefficients here as our exponents. And when we do it with concentration, this is what is sometimes referred to as Kc, right? And that means the equilibrium concentration, or the equilibrium constant based on concentration. Now, if these guys were gases, we also talked about the idea that you could write the same sort of expression, but because they're gases, we can use pressures or partial pressures. So we could say the partial pressure squared of C times the partial pressure squared of D will be equal to the partial pressure squared of A times the partial pressure to the 4th of B. And this is what is known as Kp. Any questions on that there? So again, these are the expressions that you could write to calculate either Kc or Kp. Kc and Kp typically don't equal each other numerically, so Kc typically doesn't equal Kp, but they can tell you kind of the same thing. They could tell you, when something reaches equilibrium, Do we mainly have reactants or products? So typically, if we have a large value of K, that means that when we do reach equilibrium, we would mainly have products. And that is because when we look at basically how we calculate our equilibrium, it is products over reactants. So in order to get a large number, the top guy would have to be a big number, and the bottom guy would be a smaller number, which means we would mainly have products when we reach equilibrium. And vice versa, if we have sort of a small value of K, we would mainly have reactants when we reach equilibrium. And for the same reason, in that case, we would have a larger number on the bottom where it's reactants, a smaller number on top where it's products, and obviously that would get us a smaller number. So remember that when we consider a large number for K, a big large number is 1, yeah? So anything sort of above 1 is considered sort of a large value for K. Anything less than 1 is considered a small value for K. Also remember that K has no units. So K is just usually a number, so just a number. And again, that number will tell you kind of like what we were talking about up here, whether or not we have more products when we reach equilibrium, more reactants when we reach equilibrium. Questions on that? We did talk about this stuff, I hope, yes. So any questions on that there? It's been a long layoff. Now, in addition to that, I believe that we talked about this idea of between KC and KP. Again, they don't numerically typically equal each other, but they will kind of tell you the same thing. Again, if you have a large value of Kp, that should mean that you mainly have products when you reach equilibrium. That would also mean that you mainly have a lot of probably gas molecules there on the product side, and that's contributing to a lot of the pressure for that equilibrium. And same thing with a large value of Kc. That would mean, again, you would have more products, probably a higher concentration of products at equilibrium, and that would be contributing to the higher K value. Now, there is a way to go from, which I believe we also talked about, going from, say, Kc to Kp. And there's that formula, the Kp equals Kc RT natural log of N. So I think we saw that, if I'm not mistaken, back a little bit there. So we have this relationship here that you can calculate your Kp from your Kc value. R again is our gas constant, so that's a 0.08206 value. Again, a lot of people I know round that to 0.0821, which is all good. T is our temperature in Kelvin, just like kind of normal gas sort of rules there. And as we talked about, I think we did some examples as well, but delta N is the change in the number of moles of gas molecules. And I think as we talked about in class, it's important to do the moles of our products minus the moles of our reactants. And again, you don't want to ignore. So for example, let's just say we had 1 minus 2 gives you -1. Again, you don't want to ignore the sign there, because obviously when you go into this equation up here, it is going to make a big difference in terms of mathematically what you're going to do if you had, say, just 1 or if you had -1. Any questions on any of that stuff? And correct me if I'm wrong, but we did get through all this, right? Any questions on any part of that? So I think we did some a number of examples on that. And if I'm not mistaken, I think where we sort of ended up with was talking about ways that you can manipulate an equation and the effect that it has on the k values. So let's just review that as well, just to make sure. Just go back, and I'll find somewhere to scribble. Get rid of this. I'll scribble on this page. So remember that sometimes you may be asked to find the equilibrium constant for an overall reaction, and you may just be given several different reactions. For example, you may be given A plus B goes to C plus D, and this has a K value. And then maybe, C plus D goes to E plus F, and maybe this has a K value. And maybe you're interested in what is the K value for A plus B goes to E plus F. And again, there's a couple ways we could do this. We can, add these two reactions together. Again, things on opposite sides of the arrow will cancel out, and that would leave you the overall reaction that we're actually looking for. Now, there's a couple of different ways in which, if we just take a reaction and we'll go like that, right? So in this case, if we wrote the equilibrium expression for this K would be C times D divided by A times B. But if we didn't need this reaction the way it's written, but perhaps we needed the reverse of that reaction, we would write K is equal to A times B divided by C times D. And if you look at really the relationship between these two, we could see that really the relationship is the inverse of it. So that means that if you reverse a reaction, you take 1 over the K value, and that will give you the new K value for the reverse of that reaction. So again, if say this K was 4, this K would be 1 over 4.25, obviously, when you get there, and you calculate it out. I believe without my calculator, I'll give it a try. And so if you reverse a reaction, you take 1 over the K value. Now, the other things that you might have to do as well is sometimes, kind of like, and I think we talked about this, it's the idea like Hess's law, when you add all those different reactions together to get an overall reaction. Perhaps you don't need one of each of those, but perhaps you need 2 of something. So say you multiply by a common number here. And again, our K for our regular reaction, products over reactants. And if we do it for the one where we multiplied everything by a factor of 2, we will get a K expression that looks like this. And again, the relationship between these two here is essentially K is squared, yeah? So if you basically have to multiply by a common number, you basically will take the K value to that common number. So if you had to multiply everything there by 3, you would take the K value and you would cube it. If you multiplied by 4, you would take the K value to the 4th power, and so forth. So that's another way, very common way to manipulate these equations and how it affects the K value. If you multiply by a common number, you pretty much take the K value to that common number. And we could also look at it doing the other way. Sometimes you may be given, say, this reaction with all those coefficients, and you actually just need this reaction. And when you're going in this direction, we essentially divided by 2. And when you divide by 2, we can see that the relationship going in this direction is basically the square root. And that means that if you did the k would equal basically in this case the square root of k. So if you divide by a common number, you essentially will just take the k value to that common number. So whatever that common number is, same idea. If you divided by a factor of 3 across it, you essentially would take the cubed root. You divide by 4, you take the 4th root, and so forth. Any questions on that part of it? Now, and again, if you do have questions, feel free to type in. If I've moved on, I will go back and answer your questions, okay? So a reminder up here, when we're adding these two guys together, if we wrote the expression for K1 for that first one, again, it would be C times D divided by A times B. And if we wrote it for the second one, it would be E times F divided by C times D. And again, coming back to this one here and this one. So when we add two reactions together, we actually end up multiplying the K values. So when you add reactions together, that is when you multiply those K values. So if I multiply those K values together, and I'll just do it here, if we multiply them together, what's going to happen is we have C over C times D, A and B times E and F. Whoops, keep that separate. F and C and D. And essentially when we multiply them together, these guys will cancel. And what that will give you is what we see down here, the equilibrium constant for the overall reaction, which is E times F divided by A times B. So those are all the different ways in which you can essentially sort of manipulate K values. And these are typically problems where you're given a number of individual reactions, and those reactions all have a K value associated with them. So again, just to review, if you need to add several reactions together and you're looking for the K value for the overall reaction, you're essentially going to multiply all the K values together for the individual reactions. If there's a reaction that you need to reverse, you would take 1 over the K value for that particular reaction. If there's a reaction that you need to multiply by a common number, you then would take the K value and square it. For example, if you multiply by 2, cube it if you multiply by 3, and so forth. So you basically will take the K value to that common number. And the last way that you typically can manipulate a K value is if you need a reaction where you need to divide by a common number, you then would take the root of that common number. So again, if you divided by 2, you would take the square root of it. If you divided by 3, you would take the cube root of it. Any questions on any of that stuff? I think that is everything that we talked about and kind of where we left off. If I'm mistaken, just type in there and let me know, but I think we got through all of that. Any questions on any of that? And also a couple of reminders for K. Again, the things that we do not include when we write Ks, right? So if we write our equilibrium expressions, we do not include anything that is a solid or a liquid. So that pretty much means they have no effect on the equilibrium. So that pretty much means that it is only aqueous and gas guys that are included. Yeah. So again, we don't do solids in the equilibrium expression or things with pure liquids. Again, as we talked about, solids essentially is just going to be sitting there on the bottom, really not participating in the reaction or the equilibrium that's happening. And things that are liquids, something like water, for example, usually has a pretty high concentration. It usually will remain constant throughout a particular reaction. Any questions on any of that stuff there before we continue on where I think we left off? Okay. All right. So I think where we left off, and I don't think we got to it, but even if we did, we'll just pick up there, I think. Now that I scribbled over all this stuff, let me just get to the right one. And again, a reminder, everything I scribble on the screen will be captured on the recording that will be up on our Canvas site and probably our and maybe a link there to like a YouTube video of it and stuff like that. But you can probably watch it through Canvas as well. So I think sort of where we left off is here with Q. And Q is, again, a kind of a new letter that we get to use. And it's one of the few other letters other than K that we get to use. And Q is really used for a certain situation. Q is calculated the exact same way as you would calculate the equilibrium constant. It is the products divided by the reactants. Were we really that far back? So heterogeneous equilibrium. Okay, then I just gave you a preview, I guess, of everything. Hang on. So let's go back then. Hang on, let me find that. So yeah, so it was back there. All right, then I gave you a preview. We'll go back then. Now that I scribbled through all that. So thank you very much. So we're going to get back there then. All right. Okay. So were we on this example then? Is that where we were? So did we do this example then? We did this example. Okay. Let's make sure. Thank you. So it's like 3 weeks, you know, it's a long time. All right. So we did this one. So this was the one, again, we were sort of reviewing just to go through it. This is the one where we had the KC and we calculated the KC. So we're back here, we'll just talk about it. The KC we calculated because we were given concentrations, and that would allow us to calculate the KC value by taking products over reactants. Again, we got to 220 in this case. I think if I remember, it was 216 was the actual number you got on your calculator, but significant figure-wise, we ended up at 220. And again, here's that equation that I was talking about previously. That allows us to go from KC to KP in this case. Again, when we looked at the change in the number of moles, we want to look at just the gases, and that is our products minus the reactants. So we had one gas molecule on the product side, we had two on the reactant side. Again, when you're calculating the gas molecules, you can look at the coefficients. So when we look over here, again, the coefficient is 1 and 1, so that's 2 and a 1 on the product side. And when we put it in there, we get 7.7. And again, as we talked about, you don't get the same value there for the KP and the KC, but they both do tell you sort of the same thing, that in this case, this would be considered a large value of K. And you'd be able to know that you have mainly products when you reach equilibrium. All right, so we did this example then, yeah. Okay. Did we do this example? We did as well. Okay. I feel like I remember people going to the board to do it, but maybe I might be wrong. And again, here in this case, we were looking for the equilibrium pressure. So we were able to use the partial pressures here and the Kp expression and basically rearrange it in this case to solve for PO2. And again, when we plugged in there, we see that we got something like 347 atmospheres. And again, that would also tell us that we probably mainly would have our products at equilibrium, especially with a Kp value of 158. That's a very large Kp value, which means this reaction mainly went towards the product side. And was this the one where we left off at then? Okay. So in a heterogeneous equilibrium, and thank you for letting me know. Perfect. In a heterogeneous equilibrium, again, we have sort of a combination of different states. That's essentially what it means. And when we do write the equilibrium expression, we could write it like we do here, like normal with our products over our reactants. And in this particular case, as I mentioned before, solid pretty much doesn't really participate in a reaction. Again, you could think about it like this, you got the solid just kind of sitting there, right? And in order for it to participate or be able to participate, it would have to kind of dissolve. But once it would dissolve, it would no longer be a solid, it would be aqueous. So the solid itself will have really no effect on sort of the equilibrium because it's just kind of sitting there. And that means that we can essentially get rid of anything that is a solid in this. And when we would write the equilibrium expression for this particular one, it should just be this one right here, that the equilibrium constant is equal to just this CO2. And that's because the CO2 is a gas, so it would be participating. And if we wanted to write the Kp expression for it, it would be this one here, that the Kp equals the pressure of CO2. And that's, I think, what I was thinking about. I think we talked about it towards at the end there. If we had something like something like this, and it equals, say, if you had something like this and it's just solid at the end, again, if you write the equilibrium expression for it, it would actually be 1 because that's a solid on the product side over A and B squared for the Kc. And then the Kp would be 1 over the pressure of A times the pressure squared of B. So again, if you do have something where it is a solid or a liquid or something on the product side, the way you would write the expression is take 1 over the reactants. And just like over here, essentially we have nothing that's going to be in it on the reactant side. So it just is really just the product side. And ultimately what this gets us to is sort of what we talked about just a second ago as well, that really the only things that participate in sort of the equilibrium reaction and has any effect on the equilibrium reaction are, again, things that are aqueous because they're floating around and participating with each other. Also gases for the same reason. They are floating, they're flying around and sort of participating with each other. So those are the only things that you put into the K. Again, you do not, as it says in the box down there, include anything that is liquid or solid. So these guys not included into the K expression. Any questions on that? So again, for the reaction that's on the screen on the top there, the 2 that I put in the box would be the correct way to write the equilibrium expression for both of these, either the Kp or the Kc. Any questions on that? All right. So then let's take a look at that. And again, this picture just sort of illustrates that. Again, you got some solids sitting here on the bottom, really not participating very much, in the reaction that's taking place. Basically the same picture there. So the pressure of the CO2, for example, in this container has really no effect, or is not affected at all by that solid that's sitting there. It's going to basically be able to fly around sort of freely. And again, in order for that solid to sort of participate, it would have to turn into a gas, but then it would not be a solid. So it would be included if it became a gas. And then obviously in a sort of a solution situation, the solid would need to dissolve in order to sort of participate as those guys are moving around. Any questions on that there? So I'm assuming we did not do this example either, right? So why don't you take a moment and why don't you work on this example? Yeah, I don't know. I think in the book there is some solutions to the homework problems. I'm not posting any of the solutions to the homework or anything like that, but I think some of the problems do have answers in the back of the book is where I think you would find this. So take a moment here and work this out, and then we'll talk about it. R is 0.08206. And again, since it's the equilibrium constant, unnecessary need the units. R again, you can use 0.0821. You're welcome. Okay, so let's take a look and see how we're doing. So in this case, we're looking to solve for both, I believe, the Kp and the Kc. And obviously in this problem, we're given the pressures of each gas. So it would make sense to obviously first solve for the Kp, and then we can solve for the Kc by using that formula that relates the two that we talked about a little bit a second ago. So if we were going to do the Kp in this case, it would be the partial pressure of NH3 times the partial pressure of H2S. In this case, again, because the reactant is a solid, it would not be included in the equilibrium expression. So it would just be that. And then obviously we can just plug and chug those guys in. So if we do that, it looks like we get a Kp value here of 0.0702. 3 sig figs because of the 0.265. Any questions on the first part here? Now, once we do have the Kp value, that's going to allow us to obviously have this number. R, which is a constant, and right above that is something that we already have. In this case, they did give us a temperature, which is 295. So we have that. It's actually in Kelvin, so we're all good on that. We do need to figure out the change in the number of moles, and that again is going to be the moles of your products minus the moles of your reactants, which in this particular case, again, the coefficient here is 1, and the coefficient here is 1 as well, which would give you 2 minus 0, which would equal 2 for the change in the number of moles, as on the reactant side, all we got there is a solid. Any questions on that there? So we want to rearrange that equation, and that's essentially what this is. Essentially, right, it is just Kc basically equals Kp divided by RT delta N. That's where the negative comes from because it dropped it to the bottom basically, which means it's 1 over that basically. So it's just the way they wrote it. So we do have all of those numbers. We have the Kp that we calculated above, which is the 0.0702, the R value and the T value. So we could plug it in. And if we plug it in, it looks like we get a Kc value of 1.20 times 10 to the fourth. That would be our Kc value. So as we talked about before, they're not usually the same number. But again, here, they both do tell you sort of the same idea. Here we do have a small value of K for each of them, the Kp and the Kc, which means, mainly when we reach equilibrium, we should still have reactants. Any questions on any part of that calculation? Or any questions on how to calculate Kc or Kp, and then obviously go from one to the other. Again, a reminder that the formula, like this formula up here, will again not be provided for you. So again, you do need to know those formulas, but that is obviously the way that you go from Kp to Kc. And much like these examples that we did, obviously you want to calculate either Kp or Kc depending on sort of the information that's given to you. So if you're given concentrations, probably Kc first. If you're giving pressures, then Kp. Any questions on any of that? So now, hopefully I didn't scribble too much on this page. Now I sort of we're going to talk about, again, sort of what we talked about there at the beginning that I thought we perhaps talked about. But again, there will be certain times where, as I mentioned, you will be given sort of individual sort of equilibrium reactions and equilibrium constants. And you may have to add maybe 2 equations together to get an overall reaction. You may have to add 3 equations to get an overall reaction. And when you do so, like the above example there, if we added those two reactions together, we would get an overall reaction of A plus B goes to E plus F. And if we were interested again in the K value for that reaction, using just the information from the first two reactions, as I mentioned when we first started, kind of a preview, I guess, what we do when we add reactions together is essentially we're going to multiply the K values. So when you add 2, 3 reactions together to get a new kind of overall reaction, what you do with the K values, again, is you don't add them together, you actually multiply them together. And that's because when we multiply those two guys together, it is basically the C's canceling each other out, like I did on the previous example when they multiply, and the D's also cancel each other out when you multiply them together, and you get that overall reaction. So that is one very common way that you sometimes have to manipulate a reaction that has a K value. You may have to multiply, add them together, several different individual reactions, and then you would multiply the K values. Again, this is very similar to the stuff like Hess's law that you did probably last semester, where you had all these different reactions. You had to kind of add them together to build sort of an overall reaction that you're looking for. Any questions on that there? And obviously in this type of problem, you would be given the K values for each of the individual reactions. Now, this one was something that we were talking about as well when I started scribbling. And this is basically the reverse of the reaction. So sometimes when you're doing a problem like that, where you have individual reactions that you're adding together, or before you're able to add them together, you may have to take one of those reactions and reverse them. And when you do reverse them, as I mentioned at the beginning here, if we look at this one, again, this number not too important in terms of where it came from, but if we look at this reaction, the equilibrium expression is this one, products over reactants. And if we take really the reverse of that reaction, which is what this is, right, the reverse of the reaction, we would write the equilibrium expression kind of the opposite way, because our reactants then became our products became our reactants. And essentially what you're doing is taking 1 over the K value. And in this particular example, if you do that, you'll get a value of 216 versus 4.63 times 10 to the minus 3. So in a situation where you're again trying to build an overall reaction and your goal is to figure out the K value for that reaction, if one of those individual reactions you're using, you need to flip or reverse, you take 1 over the K value and that will give you the new one. It is important to note that when you do see a K value, for example, this K value here, it is specific for the reaction as it's written and at that temperature. So if we say I have a K value of 4.63 times 10 to the minus 3, it is specific for this reaction exactly how it's written, which means that the N2O4 is the reactants, the NO2 is the products. And that is different than if I said, hey, the K value is 216. That 216 is specific for exactly how this reaction is written and at that particular temperature. And that means that 216 for the K value is specific for the NO2 as your reactants and the N2O4. So when we do see a K value, it is specific for exactly that reaction, how it's written, and the actual temperature it's at. Any questions on reversing a reaction and the effect on the K value? Now, unfortunately, I think we're going to get to where I started scribbling, so hopefully we'll be able to still see it maybe. That's good. So a couple reminders that when we do write equilibrium expressions, the K value We could write the Kc value, which is typically everybody in molarity. So again, that is what we mean when we do put those little, kind of brackets around C and stuff like that, right? The brackets mean concentration. And obviously that means molarity, which is our moles per liter, right? So that's typically what we mean when we see those brackets. We can do it in atmospheres as well. So in this chapter, we'll talk about sort of doing calculations and ice tables and stuff like that. Atmospheres is the pressure unit that you do want to typically use, especially when you're doing calculations. So even if they ask you to give in something like torr or millimeters of mercury, and they give you the pressures in those units, typically, especially if you're doing a calculation, typically you need to convert it to atmospheres, do the calculation, and then convert it into something else. As we talked about, we don't include our solids or liquids, again, because their concentration remains pretty constant. It doesn't really change that much during the equilibrium or the reaction is taking place. And for the most part, you don't really have units associated with K. It is just a number. And that number, again, tells you whether or not when you reach equilibrium, do you mainly have products or do you mainly have reactants? And as I was mentioning, number 4 there, when you do see a value for the equilibrium constant, it is specific for the equation that you're looking at, exactly how it's written, whatever's on the reactant side, whatever's on the product side, and for temperature. So as we'll talk about, temperature is the one thing that can sort of affect the actual value of the equilibrium constant. Nothing else will really affect the actual value of the equilibrium constant. The only thing that will affect it is if you actually change the temperature. So if you keep the temperature constant, you could start with a wide variety of starting amounts of reactants and products. It will always come to the same value for the equilibrium constant as long as you keep the temperature constant. But if you vary the temperature, then you will actually see a different value for the equilibrium constant. And again, as we talked about, a couple ways to manipulate them. If you need to add multiple reactions together, you then multiply the K values together to get the overall K value. And if you need to, I'll just come back to what I wrote. I think this is going to be a little messy here. If you need to reverse a K reaction, a reaction that has a K value, then you would basically take 1 over the K value. So we'll just look at the scribble I did at the beginning, which was kind of a preview. Again, just to remind, as I was talking about, the other sort of situation is what we were talking about down here. And down here, as we can see, if you do need to multiply by a common number, basically you would take the K value to that common number. And if you had to divide by a common number, you would divide the K value by that common number, or take the root of it. I guess not really divide, but you would take the root of it. So like our example down here, let's switch out colors maybe. Go with red. So as like we saw down here, this is the other 2 common things that you have to do. If we multiply by 2 all the way across a common number 2, essentially we would square it. And like I said, if you need to multiply by a common number of 3, you would cube it and so forth. Or if we're going in this direction, again, if we're dividing by a common number of 2, for example, we would take the square root of it. And if we divide by, say, the common number of 3, we would take the cube root of it, if we were dividing by 3 and so forth. So those are really the maybe 4 ways that you typically would need to manipulate individual reactions or equations in order to add them together. So usually this will all be involved in a problem where, again, you're given an overall reaction and you're given several individual reactions, and you're asked basically to figure out the K value of the overall reaction. So before you can add those individual reactions together, you usually will have to do some type of manipulation, either multiply by a common number, divide by a common number, or maybe reverse a reaction. So you want to, much like probably what you did with Hess's law, you want to keep track of everything that you did. You want to adjust the K values accordingly. And then probably the last thing that you would do would be multiply the K values together after you did each of the adjustments. And just like in Hess's law, there may be some reactions where you don't have to touch it. You could just use it just the way it's written. And then obviously you would do nothing to the K value for that one. It would just remain the same. Any questions on any of that stuff? How to manipulate K values, how to adjust them, and then basically add them, all of those reactions together? Okay, and again, at any time, feel free to type a question into that chat. Like I said, even if I've kind of moved on, I will see your question and I will go back and answer your question for sure. Okay. All right. Then I think now I'm going to go through this here. And again, I apologize, but on your notes, you'll actually see what it says. Before I got crazy and started scribbling all over. There you go. And what I just went through is essentially what we just were talking about, how to manipulate equations. So now I think we're back here, if I'm not mistaken. All right, so we're back here to our Q, which is what is known as the reaction quotient. And Q, like I said, is one of those letters we get to use outside of K. But Q is really calculated the exact same way as we do calculate K. So when we calculate Q, it is calculated the same as K. So if we were to calculate Q, we would do it the exact same way or write the expression for Q. That also means that we would still use the coefficients as the exponents. So if we were to do Q for the above reaction, we would still take C to the C, which is the coefficient, divided by A to the A and B to the B here. And the reason that we use Q is for a couple of reasons. We use Q to help us determine a couple of things. We use Q to determine, are we at equilibrium? And the reason that we use Q to figure that out is usually what we're given a lot of times are kind of initial concentrations. And if we're given the initial concentrations, we could use Q and the value of K to answer that question, are we at equilibrium? And we could also use it to answer the question, if we're not, which way do we need to go to reach equilibrium? So Q oftentimes is used to sort of answer those questions. So Q, sort of a straight Q type problem, is pretty much that question. They will give you some information and they will ask you, is this system at equilibrium? And you can use Q to answer that question. And the second part of that question usually is, if it's not at equilibrium, which way does it need to go to reach equilibrium? Does it need to go to the right, which would mean it needs to make more products to reach equilibrium? Does it need to go to the left, which means does it need to make more reactants to reach equilibrium? Or it could actually be at equilibrium in that case. So if you calculate Q, like we show here, and it is greater than Kc, what that first tells you is it is not at equilibrium. And in order to reach equilibrium, it pretty much needs to go the opposite way of where that's pointing. So it needs to go that way towards the reactant side. And it will need to go towards the reactant side to reach equilibrium. Now, if you calculate Q and it does equal K, that means that that system is at equilibrium. So obviously it doesn't need to go any way to reach equilibrium. You do have a system that's at equilibrium. And lastly, if you calculate Q and it's less than K, again, it will go opposite the way it's pointing. So in order to reach equilibrium, you would need to go to the right and make more products in order to reach equilibrium. So clearly, the only way that you could calculate Q is you need to be given information about everybody. Yes. Because if you're not given information about everybody in that particular reaction, you have no way to calculate Q. So that is a big flag. If it's, for example, not a Q problem, but somewhere along the way where you might want to calculate Q just to make sure is when you're given pretty much the starting amounts of everybody. Because you're given the starting amounts of everybody, that would imply obviously the reaction is taking place, right? So there's forward, there's backwards. So because you have the kind of initial concentrations of everybody, that's when you definitely want to calculate Q, because that'll allow you to figure out, are you at equilibrium, which way you need to go to reach equilibrium. Any questions on Q? And obviously in this type of problem, the K value, if it's a straight Q problem, the K value will be provided for you usually in the problem. So you'll have that K value available to you to actually compare the Q value that you calculated. Any questions on that? All right, so I think we may have a problem here. So why don't you give this a go, see what you come up with. So take a couple minutes and then we'll talk about it. So we have this reaction that there are 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and 6.42 to the minus 4 moles of NH3 in a 3.5 liter. The K value is 1.2. The question is, are you at equilibrium? And if you're not at equilibrium, which way do you have to go to reach equilibrium? So again, take a few minutes and kind of work on that, and then we'll go through it. Okay, so let's take a look and see how we're doing. So first off, this is a very common sort of Q question. You can see that they do provide you with the K value. So obviously we were going to eventually want to compare our Q to our K value and determine whether or not A, the system is at equilibrium at this point, and B, if it is not at equilibrium, which way it needs to go to reach equilibrium. Now, to calculate Q, again, it is done the exact same way as we would do K. So we would take our products, which in this case is NH3. We would need to square it because of the coefficient that we see. We would then have to divide it by the concentration of N2, which the coefficient is 1, so we do nothing to it. And then our H2, which again, we want to make sure that we take it to the third there because of the coefficients that are there. Any questions on how we get to Q in terms of the expression? Now, a couple other things here in this problem, a little bit different is we're not given the concentration, but we are given the moles, and we do have the volume, which is the liters. So obviously, before we can go into the Q expression, we do need to convert everybody, into molarity first. So that's the first thing that we're going to do here. We're going to take each of those guys and basically convert them into molarity. And I believe if you do each of them there, you get the numbers that we see. 0.0711 for our N2, 0.00917 for our H2, and then 0.000183 for our NH3. At this point, again, we have everything that we need to go into our Q expression. And that's, again, what we see down here. So we have our Q, which again was the concentration of NH3 squared divided by our, again, 2 and our H2. And again, we're going to be cubing our H2. So that gives us a value of 0.611, which would be our value for Q. Any questions on that part of the calculation? So again, it's important that once you get the Q value, you want to compare it to the K value. So the Q value that we got was 0.611. I believe the K value was 1.2, if I'm not mistaken. So first off, we see that Q does not equal K. So the first thing that tells us is we are not at equilibrium. Because again, Q doesn't equal K. And in this particular case, we see that Q is less than K. So again, if you put Q on the left and K on the right, it will go opposite the way that little sign is pointing. That means in order to reach equilibrium, we need to go to the right and basically make more products. Any questions on that calculation? So I would call this sort of a just a straight Q type problem, and it's a very common problem that you come across. Is really to answer those two questions: A, are you at equilibrium? And B, if you're not, which way you need to go to reach equilibrium. We will see a little bit later on in this chapter another place where you can calculate Q, and you maybe should calculate Q, and it has to do with when we start figuring out equilibrium concentrations. But a lot of times you'll get just a problem that's sort of just a straight problem like this. Any questions on that calculation? Okay. So then let's talk about how we actually do solve equilibrium type problems. So as I mentioned before, you could calculate Q if you're given the initial concentrations of everybody. And you should always, when you're given sort of the concentrations of everybody in the reaction. Now, sometimes you're given just the initial concentrations of, say, your reactants. Sometimes you're given the initial concentrations of everybody that's in the reaction. And remember that when we do solve for K, or want to get a value of K, and we put those guys in our products divided by our reactants, the values that we have to put in here is they have to be equilibrium concentrations, our equilibrium pressures. So remember that if you don't have the equilibrium concentrations or the equilibrium pressures, you actually will have to solve for those. And the way that we commonly will solve for equilibrium concentrations is, if we're given just the initials, is we will use what is referred to as ice tables. Yeah. And some people maybe have used ice tables before. You could use it sometimes when you do things like limiting reagents or limiting reactants. But what ice tables mean is initial, change, and equilibrium. Go down the whole screen there with it. So initial, change, and equilibrium. And if you used it for something like limiting reagents, it's maybe initial, change, and end, but it's sort of the same idea. So when we do have something and we want to do like a, go this way, get rid of this for just a sec. So if we do have something and we want to do an ice table, so say we have a reaction like 2A plus 3B gives us 2AB, right? In this particular case. And let's say you were given that you're starting with an initial concentration of A of 2 molar and B 3 molar, which we're not going to solve for anything. So when we would do our concentration or our ice table here, initially we would put in our values of 2 for A. We would do 3 there for B. And if you're not given any concentration for your products, it is usually pretty safe to assume that initially you would have 0 for that guy. So again, if you're not given any initial concentration of anything on the product side, it's pretty safe to assume that you got 0 to start with. If you are given a concentration here to start with on the product side, and you have the concentrations to everybody, that is where you should at some point calculate Q, just to make sure you're not at equilibrium, but more importantly, which way it needs to go to reach equilibrium. But if you're not given anything on the product side, safe to assume 0. Also would be safe to assume that the reaction is heading from reactants to products in that case. And that's really where the change part comes in. So the change part of the ice table is really important. It does two things. It helps you to decide what is changing. So how much concentration is changing, either decreasing or increasing. So if we go under this assumption here that we're going from reactants to products because we weren't given any products to begin with, what that should tell us is the amount of reactants should decrease. And the way we represent that is with a minus. While we should expect, if the reaction is heading towards the products, that the amount of products should increase. And we would represent that with a plus. So typically when we do an ice table, we use a variable, and that variable is x. And here we would do minus 2x, minus 3x, and plus 2x. And where we get those numbers from is the actual coefficients in the balanced equation. So when we look at the balanced equation, we have a 2 here, we have a 3 here, and we have a 2 here. And that is what these numbers are for. And that's where those numbers come from. And those numbers come from the coefficients. And really what that is allowing you to do is take into account everybody's favorite thing, stoichiometry. So it's able to take into account the mole to mole relationship. So basically the stoichiometry. And it does that for you by putting those coefficients. So that's really important here when you're doing an ice table. A, it's got to be a balanced equation, which in our case, usually it is. But B, you do have to put those coefficients in, because if you don't, this part of it will be wrong. So the mole to mole relationship, really the stoichiometry part of it, will be wrong, and you will end up with the wrong answer there. Any questions on that part of the ice table? Now, what we do here is then pretty much we get to E, which is equilibrium, and we essentially are going to bring down everything. So we would have 2 minus 2x. We would have 3 minus 3x, and we would have just 2x at this point. Any questions on sort of the ice table or where any of those numbers came from? Now, this is really where the math is going to come into play. We could write the equilibrium expression for this, which is our products over our reactants. And let's just say up here, they also gave you the K value was 20, for example. So that value would usually be given to you as well, the 20, for example. And what we're going to do is essentially then take everything that we have at the equilibrium line, and we're going to substitute it into that K expression. So that'll give us 2x squared divided by 2 minus 2x. Also, it has to square it in that case. And that would be times 3 minus 3x, which we would have to cube it in that case. And then this is where all the fun math comes into play, right? So you got to do some foiling and all that good stuff and some distributing. So eventually what will happen is you would solve for x. So mathematically you would solve for x, as we'll talk about probably next time. You could do something perhaps like the quadratic formula. You may be able to do a perfect square, some other ways to solve for x. But mathematically, you'll eventually solve for x. And x would represent the change part. So what you would do is you would come back into here and you would put the x into each of those. And then that would allow you to actually get the equilibrium concentrations of each of those guys. You'd be able to get the equilibrium concentration of A, equilibrium concentration of B, and the equilibrium concentration of AB. So that's essentially how an ice table works. You put your initial concentrations in, you do the change part, minuses usually on the reactant side to the products if the reaction is thought to be going towards the product side. You do want to take the coefficients into account because that will take care of all the mole to mole relationship. You then would take your equilibrium line from your ice table, put it into your K expression, do some fun math, and solve for x. Once you get the x is really not the answer. You then have to go back again into your equilibrium line, put x back in there, and that will allow you to get the concentrations of everybody at equilibrium. Any questions on that there? All right, so I think maybe that's a good stopping point for today in our first real lecture. Any questions on anything that we talked about today? So a couple of reminders. We are going to take the dreaded quiz that's been postponed now for chapter 12. And we're going to take that on Tuesday. So it will be available for you to take on Tuesday. I will give you some more information, but my gut feeling that now is it will be available. We will have lecture on Tuesday like normal, and then it'll probably be available maybe during lab time, and you can take the quiz at that point. It will be done through Canvas, so you will have to log into Canvas, obviously. You can take the quiz. It will be timed. You probably will need some paper and a calculator to show your work, and then you'll need to upload. There'll be a link for you to do so. Upload your work. That way, again, if you type in online the answer wrong, at least I could give you some partial credit and all that kind of stuff. So it'll cover just chapter 12 like it originally was planned to be. And again, like normal, you'll be provided constants and stuff like that. But again, no formulas or anything like that. Any questions on the quiz that's coming up on Tuesday? And like I said, before Tuesday, at some point, I will give you some more information about where to get it and access it and all that kind of stuff. Okay, so we're going to continue lecturing on Tuesday on this topic, hopefully. And that also means that pretty soon the first exam is coming up as well. So it covers through this chapter. So we got to go through ice tables and do some problems and some Le Chatelier's principle. And then we should be done with this chapter. For today's lab, we're going to be doing, like the new schedule says, it was the one we kind of left off on, which is, I think, psychokinetics activity. So what I'm going to do is we're going to take a little break here between lecture and lab, and I'm going to stand and stretch. Maybe you should as well. And I'm going to open up the lab meeting at its normal time around 11:30ish. And what I'm going to do is I'm going to talk a little bit about the lab, some weird things in there that you might have questions on. And then I'll hang around for a while. Again, if you have questions, you could pop in and ask and stuff like that. But at the beginning of lab, when we start, I'll try to go over a little bit on that because there's some information about pseudo rate constants and that type of stuff that I think you need to maybe have an idea as to what to do. And we'll talk about that experiment. So you should be doing today, which is the kinetics activity. It's essentially a lot of graphs that you have to make through Excel. And I'll talk about some of the calculation parts or things that you need to do to be able to answer the questions and stuff like that. Any questions on any of that stuff? Okay, so again, we'll take a little break about 11:30ish. I'll be back, and you should probably pop in as well. Again, at the beginning there, I'll talk a little bit about the experiment and some of the calculations that you might not be familiar with that you need to do. And also a reminder, the iodine one, the previous experiment is due, I think, next Thursday, I think is when it's due, if I'm not mistaken, maybe. I feel like the 9th, I have that date in my head. So it should be on Canvas. Again, if you go to the modules section, there should be a place where you could click and upload your lab report. Again, probably that PDF file would be the best way if you could do that. Again, something like Adobe Scan, I think, has a free phone app for iPhone and Android, or any type of app like that would probably be the easiest way to do that for you. All right, any questions before we officially kind of end the lecture part? Okay, I'll probably see you in a little bit around 11:30ish. So we'll end the lecture part now. Have a good little break. I'll see everybody in a little bit.